Right, so we are now live in Facebook as well as in YouTube. So the first thing that I'm going to discuss with you will be moment of inertia. Okay, so in moment of inertia, say I have here an I-beam and the dimensions are given. I have 5 meters for this length. I'm just using five. The meters will be the unit, but it is a bit how do you call? It's not realistic, but this is just for discussion purposes. And then we have two in here for the height, and then these are the dimension of the I beam. Two here, two there. This is of course 5. This is 2. If you can see what I'm pointing at, this is 2 as well. This will be 5. This is 2. This is 2, and this is 2. Okay, right. So this is just for discussion, right? What can we do here to find for the moment of inertia? What is this, by the way? Moment of inertia is the resistance of a body against rotation. So first off, if you have this one, you must know where your centroid is. So what we're going to do here is to find for the moment of inertia about the centroid of the whole composite shape. So I'm going to change that to find the moment of inertia about the neutral axis of the shape. Okay. Now I have here a table. The moment of inertia for a rectangle is 1/12 the base times the height. And then for triangle is 1/36 the base times the height. As you can see here from the orientation of the shape, the base is for the rectangle, it will be at the bottom, and height will be the length when it is in upright position. And then for triangle, it should be the base should be parallel to the surface that it had been lying on. So, for example, if you have a right triangle, then this will be your base. This will be the height. Or if it's this, base here, height here. Or if it's like this will be the height, and this will be the base. For circle, as you can see here, for rate, if you're using radius, it will be pi r to the fourth over 4, or it will be pi d to the fourth over 64. Okay, so now we're going to calculate the moment of inertia about the neutral axis of the I beam. So I will draw it again. Right, we said that it's 2 meters, 2 meters. All the short distances will be 2 meters, and the long ones will be 5. Okay, so let's assume that our neutral axis is here, because it's symmetrical though. You cannot just you can already determine where the neutral axis is. So let's say this is the x axis for reference. This is your y for reference as well. So from the x-axis, it will be, because the I-beam anyway is symmetrical, so you have a height of 2, you have 5 in here. So that will be 2. This is 5 and this is 2. So it's 9. 9 divided by 2, that will be 4.5. So half of the 5 in here, this is where your neutral axis is located along. There you go. This is your neutral axis. That is where your CG would be. And for the Y, hang on, I will do like that, yeah. So this is your Y, this is your Y bar. And your X bar will be, how far is your CG from the Y-axis. So this will be your X bar. And this is where the CG of the shape is. The X bar is 2.5 meter because this is in total 5. Can you see what I am painting or what I'm putting a green line on? So that's a total of 5, and it is at the middle. It bisects the shape. So that will be 2.5 from the y-axis, and the y bar will be 2.5, 4.5, 4.5 from the x-axis. Now, after locating the CG, so that's the first thing you're going to do, okay? First is locate CG of the composite figure. So this is done. We have already located it. That's done. Okay, the second part is you have to find for the moment of inertia of each of the shape. Right. Hello, Myra. I'm in my YouTube. I am doing my live. I'm in white because we will have our second, second, right? Yeah. No, it's not Advent. This is our first aguinaldo. It's an anticipated mass. Yeah, sorry for that. Okay, number 2. Number 2 would be compute for the I. Compute for individual moment of inertia. How many shapes do we have here? There are 3 shapes. Okay, so let's have the first one. There are 3 shapes here. One is the rectangle. Okay, I will use another color for that. One is the rectangle. 2 is upright rectangle in its upright position. 3 is the same as 1. Okay, so I1 would be, let us look at the formula. Here you go. It's 112 base height cube. Moment of inertia has got unit to the 4th. Okay, so if your B is millimeters, your H is millimeters cube, then you will have millimeters to the 4th. Okay, mm to the 4th. Okay, so because we only have rectangles in our shape, then we'll be using 112 base times height. I1 and I2 on their own neutral axis will be 112, the base is 5, and the height is 2. These are all in meters, so that will be 10 divided by 12. Okay, let's calculate that. There's a cube there, base times height, cube, okay? So we have 2 cube is 8. 8 times 5 is 40 divided by 12. All right. So that would be 3.333 meter to the fourth. Now, in actual dimensions of moment of inertia, it's actually in scientific notation because these are big ones, like 5 times 10 to the 6 millimeters to the fourth. So to make calculations easy, I just did it like this, okay? This is just for purposes of discussion, right? More often, it's millimeters in unit. Right. Now, we do moment of inertia 3. Moment of inertia 3 is when your rectangle is in upright position. So this is 2 and this is 5. So your base this time, 112, or your base is 2, and 5 will be your height, which will be cubed because it's 112. The base height is the formula. So I for rectangle is 112 BH cubed. Okay, so let's calculate it. Um, it's 112, 1 divided by 12 times the base times 5 cubed. There, okay? So it's 20.833, 20.833 repeating m to the fourth. All right. So this is step 2, compute individual I. Okay. The third one now is to use, you now compute for the I about the neutral axis. So here you have to use the transfer formula. Okay. So transfer formula is, hang on, I'll insert a new window. Okay. There you go. So the third one is, this is now what we are looking for. Moment of inertia about the neutral axis. Let me just do a landscape orientation so I will have more space. Okay. So moment of inertia about the neutral axis is equal to, for the first one, I1 plus A1 D1 square. Okay. Plus, you have I2 plus A2 D2 square plus, because there are 3 shapes altogether, I3 plus A3 D3 is square. Right. So it seems that we still have to learn, or we still have to find out or compute A1, A2, and A3. But because these are all rectangles of the same shapes, then our A1 is equal to A3, A2 is equal to A3. Now, A1, or simply A, or the area, they are the same. Our shapes are like this. Yeah? The shapes are, this is the longer side, 5 meters, and the shorter side is 2 meters. So the area will just be 10. 5 times 2 is equal to 10 meter square. Now, the struggle here is the D1. The D1, the D2, and the D3. Okay? But you have to listen very carefully. What is D1, D2, D3? The D1, D2, or D3 are the distances of the CG of the individual rectangles to the neutral axis. So let's go here and let's find out where is D1, where is D2, and where is D3. Right. Now, this is the CG of the first rectangle. The CG distance from its bottom is 1 because it has a total of 2 height. Okay, so the CG will have a distance from the CG of the whole shape. This is 2.5 because this is 5 altogether, divide by 2, so it's 2.5. Therefore, our D1 will be 3.5. Okay? Our D2 is exactly here. There's no transfer because it is exactly on the neutral axis. So D2 here is 0 because the CG of D2 is where the neutral axis is, how will I say it? The neutral axis is exactly through the CG of rectangle 2. Okay? The CG of rectangle 2, I repeat, is where your neutral axis was drawn, and that is exactly where the NA, the neutral axis of the whole shape, is. Okay, there's no distance, it's 0 distance. And for area 3, this is the CG of area 3. So how far is your CG to this distance? It's 1, correct? 1 meter. And then to your CG of the whole shape. So this is 2.5. So it's 3.5. D3 is 3.5. All right. So 3.5, that is 3.5 plus. We did not include anymore this one here. 3.5 from here until here is 3.5. From here until there is also 3.5 for D1, 3.5. And then 3.5 plus 3.5 is 7. And then you have the remaining 1 meter here, which we did not include. That's 8. We have 1 meter here, which we did not include. That's 9. So the total height of our I-beam is actually 9. 5, 6, 7, 8, 9. So we are correct. Okay. So let's go back to where we are trying to compute our moment of the inertia. Okay, moment of inertia. All right, so let's continue now. We know D1, we know D2, right? Okay, we know D1, it is 3.5. It's CG to the neutral axis. And then D2 is 0. And D3 is the same, 3.5. Why is it that they have the same? Because they are symmetrical. Okay, so now we'll just have to substitute the INA. The moment of inertia about the neutral axis of the whole shape will be I1 is 3.333 repeated plus its area is 10 and its distance is 3.5 square. The transfer formula of I1 is the same as I3, so I will just double it. Okay, I1 is equal to I3 about the neutral axis plus our I2, wherein I2 is 20.833, and then plus the area, they have the same area 10, times its distance is 0 is square. AD square is the formula. So when that is 0, 10 times 0 squared, that will be 0. You only have 20.833 remaining. So the INA, moment of inertia, this is the how resistant your shape is against rotation. The value would be, let's calculate. So that is 3.3333. I'll put 4 decimals because that's anyway repeated value, plus 10, I'll put a bracket, times 3.5 square, and then close. That will be I1. All right. And then you have to multiply it by 2. So let's do equals one time. Times 2, because this will be for I1 and I3, 251. And you have to add 20.83333. Let's do, no, 4 decimal place only. So the answer would be 524.1665 m to the 4th. All right. So that is our moment of inertia about the neutral axis of the I-beam shape. Okay, I-beam like this, having the dimensions of 5 by 5, 2 by 5 on its flanges. Okay, flange is this one. Okay, 2 by 5. And the 2 by 5 will be the I at the middle, and then another flange which is 2 by 5. Okay, so that is the I and A, moment of inertia about the neutral axis. Now we're going to shift to loadings of beams. There are 3 topics in this video, because I promised my students that I'm going to discuss to them the 3 topics that we were not able to reach because of the typhoon, and they are also included in the exam. Okay, so now the loadings on beams. Where are they? All right, anyway, I can just do it. Loadings on beams, here you go. Let's insert. You just have to type in, my dear students, you just have to type in, if you have some questions, type them below in my YouTube channel, okay, not in my Facebook. All right. I will discuss loadings on beam very briefly. Right. The very common loadings on beams are, we know what beams are, yeah? If you can you see that? That is where the supports, the skeleton, the frame of a building is, okay? So that's actually the frame of a building. Say this is the beam, and you have a column here. Yeah? And this is, for example, this is the ground floor. All right. So I'll just make it like that. So this is the beam that I am talking about. I know that you know this very well, but of course the analysis that's the one that you are missing. For the beam, it will have, because this is a column, then there will be a force on the column to carry the beam. And they are represented by my R1 notation, or variables R1 and R2. You call this one reactions of the support to whatever load you have on your beam. Loadings on beam would vary. There could be like a concentrated load. Okay, you have this examples in that PDF file that I sent you. A concentrated load is the one that is loaded in a beam, and it is pointing on the beam, just one point. There's only one force pointing on the beam. Say this is 5 newtons. Okay. We also have what we call uniformly distributed load. Uniformly distributed all right, I write it here, down here. Distributed load. Uniformly distributed load are parallel forces acting downwards. They have the same intensity. So we're not going to count anymore how many forces are going down. We just have to get the intensity. What is this? How many forces are acting per meter? So that if this is, for example, 10 Newton per meter, and the whole length is, say, 2 meters, then to get the resultant of the parallel forces, you just have to do 10 Newton per meter times times 2 meters. If you're going to look at the units, the meter and the meter cancels out. So you are only left with 10 times 2 in a Newton unit. So 20 newtons will be the resultant of the concentrated load that is spread out in a 2-meter span. And where is it acting? It will be acting at the CG of the rectangular shape. That is the resultant of the 10 Newton meter across the 2-meter span. So that will be 20 Newton force. But we are not going to get the resultant when you are going to do the Shear-Moment. But let us do the loading meantime. Another very popular load would be the triangular loading. Triangular loads, they can also be called as, if you have uniformly distributed load, they are the same as uniformly varying loads. Okay? They are uniformly varying loads. Why uniformly varying? Because you start from 0 and then it will intensify. Okay, it increase and increase and increase until you get the maximum intensity. So it varies from 0 up to, for example, this is 5 Newton per meter. Okay, so what we will do, we're going to load our beam with that intensity. Oh, by the way, if you're going to ask me what are the real life representations of our loadings on beam, for the concentrated load, it could be like a post, in a building. So for example, that is a beam and there's a post. This is a beam and there is a post in here. This post will exert a concentrated load to the beam. And the uniformly distributed load could be live loads. we can just imagine, for example, a floor, yeah, in our classroom, for example, and you guys will be seated here. Hang on, I will make that bigger. You're seated here, seated there. So all the students are seated like this, yeah? In this floor, there will be uniform distribution. It's uniform because the chairs are on the same distance apart, yeah, unless you're going to mess up with the chairs. So they will be located everywhere, or, they're around the place in our classroom. So in, but if there are only minimal difference of distances, then you can say it's uniformly distributed because there are forces that are acting on the floor in this scenario. And if you're going to put that in a rectangular shape, they are pointing downward on your beam. So it will be like this. That's why they are uniformly distributed. Now, not only that, the slab, the cement that makes the flooring, what more? Your the finishing of the floor finishing, the tiles, those are all uniformly distributed load in a beam. How about triangular loading? Triangular loading would represent water, especially for water tanks. Water are not actually waters, or water is not actually a uniformly distributed load. It is triangular in loading because of the pressure. The pressure of water is highest at its bottom. So if you have, for example, a shape of a cylinder where you're going to store your water, hang on, let me just remove all these writings here many times. So I can use this little space here for illustration. Say you have a cylinder and this is filled with water, a tank, yeah? Cylindrical tank. The pressure is highest at its bottom, okay? So it is highest at its bottom. We can illustrate it this way. Hang on. We can do it this way. Hey, it is not writing. There. Okay? It will be highest on its bottom. From the formula, the pressure is equal to rho GH. How high is the water? The G would be the acceleration due to gravity. The rho is the density of the water, 1,000 kilogram per cubic meter, and then the pressure. How will you get the force in there? The force is equal to pressure over the area. Okay? So meanwhile, let's not deal on this one because this will be taken up in your fluid mechanics. Okay. So the triangular loading, its CG is at 1/3. You know that from the centroid, center of gravity, how do you call, centroid center gravity topic. Okay, so let me just make that very thin. Okay, from its centroid till here, that distance is 1/3 the base. Okay, and if we're going to draw the resultant, it will be, let's change the color. There you go. This is the resultant of the triangular loading. Triangular loading will have an area of, you can compute for the area, same as the 20 newtons. It's 10 times 2. Okay. We will be using 2 here as well as our span. Okay. So the area will be 1/2 the base, which is 2, and the height, which is, I did not give you yet, the height, let's say this will be 15 Newton per meter. So 1/2 the base times the height, 15 Newton per meter. 2 here is in meters. The meter and meter cancels out. You're only left with Newton here. The 2 and 2 cancels out as well. So you have 15 newtons at the CG of the triangle. Okay. So those are the loadings on a beam. Now, having all this, we can now solve for the reactions in our beam. Okay, so let's draw the beam again. The equivalent loading now would be, you have your reaction here, R1. You have your reaction here, R2. And at the middle, you have the concentrated load of 5 newtons. And here you have, this is 2 meters, right? And this is 2 meters as well. And the 20 newtons is here as the resultant of the uniformly distributed load. And the triangle will be here, which is 1/3 from here, 1/3 of 2. Or it is 2/3 from here, 2/3 of 2. Okay? Because in a triangle, the CG is located 1/3 the base and 2/3 on the other end. Okay? So this is 15 newtons. So if we're going to take summation of moment at R2 to get for R1 and equate it to 0 for equilibrium purposes, clockwise positive, you have 4R1 is equal to, clockwise is equal to counterclockwise. You have 15 times 1/3 of 2, and then that's 15 times 1/3 of 2, 5 times 2 plus 5 times 2 plus 20 times, this is 1 meter because it's 2, half of it. So 2 plus 1 is 3. 20 plus 3. Okay, let's calculate. R1 will be equal to, you have, by the way, we can simplify this meantime. The 3 and the 15 will be 5 in here, so that you will have only 10. So 10 here, and then plus 10, plus 10, plus 60 is equal to, divided by 4, will be 20. So it's 20 newtons. Now, I will not make this calculation long anymore. The next will be summation of forces vertical. If you are sure with your R1 equate to 0, forces going up will be positive. So we have R1 plus R2 is equal to 20 plus 15 plus 5. 20 plus 20 will be 40. Knowing R1 equivalent to 20, so you have R2 will also be equal to 20. Okay, so 25 plus 15, 25, 30, 40. Okay, so that will be 20 and 24, R1 and R2, if you're going to look for the reactions. Okay, the only topic that is remaining is the Shear-Moment diagram. So we're going to finish it from here. I will continue with Shear-Moment later. Bye.